Over the years, computer technology has improved a lot. Along with it is the increasing resource demand of modern applications aiming to provide seamless user experience. One main factor in good computer performance is the ability to manage resources, mainly in a computer's efficiency in time-shared systems. A good CPU scheduling algorithm plays a vital role for a system's performance. In this video, I will present a modified version of the round-robin algorithm named Optimum Dynamic Time Slicing Round-Robin by Muhammad Hafiz and Farhan Rashid. Round-robin is a popular algorithm known for its simple and fair nature. This algorithm schedules process in the ready queue to use the CPU resource for a time interval called quantum. The idea of round-robin is to give equal opportunity for all processes to run at a quantum time by preempting. When a running process is not yet finished but has used its time interval, the next process in the ready queue will have access to the CPU, and the previous process will be moved back at the end of the list. This preemptive behavior leads to expensive context switches, the time spent on administrative overhead, which is a waste of CPU time. Short quantum lowers the CPU efficiency due to many context switches, but having longer quantum may lead to poor response on short interactive requests. Performing context switching only when it is necessary is an improvement to this algorithm. The authors modified the round-robin's quantum time by setting it to the median value of the sorted processes in the ready queue. It dynamically recomputes the time quantum every time a new process enters the ready queue. It logically skips a preemption step when the remaining burst time of a process in the CPU is less than the quantum. Processes with burst time smaller than the quantum gets executed until they finish, eliminating a context switch, thus improving the original round-robin algorithm. At step 1, initialize the ready queue. The processes are placed in the ready queue by the long-term scheduler. At step 2, the algorithm defines a loop for a check whether the ready queue is empty or not. If the ready queue is not empty, perform the following or remaining task. At step 3, sort all the processes in ascending order with respect to their CPU burst time and then calculate the median value. If the number of processes are odd, simply select the middle value. In case the number of processes are even, select middle plus 1 value. Step 4, set the time quantum equal to the median value. At step 5, start the execution of the processes in the ready queue. The first process in the ready queue will get the CPU. Each process entering the CPU will get the time slice defined by the median value. After getting the time slice, if the remaining CPU burst time is lesser than the median value, the process in the CPU will execute until its completion. Otherwise, the process will free the CPU and will be placed at the end of the ready queue. The next process in line will get the CPU. Lastly, at the end of each iteration, the algorithm will check the flag value. If the flag value is true, this indicates that one or more processes have returned from the block queue to the ready queue. In this case, it will sort the ready queue in ascending order with respect to their burst time, and again, a new median value will be computed. This new median value will be assigned to the time quantum. In case the flag's value is false, the program will continue its execution until all the processes are completed. Here is the code of the modified round-robin. Next, we will compare the pseudocode with the actual code. Here's the initialization, the while loop, sorting of ready queue and calculation of median, setting of time quantum, for loop for the execution of processes, and lastly, the flag checker. Here is the Gantt chart of the given example. The processes 6, 2, 3, 7, and 1 were able to execute until completion without a context switch. This is the result of the program execution. Response time, turnaround time, and waiting time are few of the metrics used to evaluate operating system scheduling algorithms. First, response time is calculated by simply subtracting the time of the user request from the time of the initial reply. To see more of a trend over time, we calculate the average first response time by dividing the sum of all response time by the number of processes. Turnaround time is the total time taken between the submission of a process for execution and the return of the complete output to the user, or simply, it is the completion time of a process, while waiting time is the amount of time a process waits in the ready queue. The table shows that the modified round robin significantly improved the average response time, turnaround time, and waiting time. Response time was reduced by 12 milliseconds, while turnaround time and waiting time were reduced by around 23.57 milliseconds. For visualization, we have here the graph representation of the previous table. Let's have another example. In this one, processes arrive at different times. After sorting, the median is set to 20. Processes get executed one by one, but then some new processes arrive in the ready queue. This triggers the flag and causes the program control to jump to step 2, which sorts the queue again and recalculate the median. This is the result of the program execution of the example. Process 2 was able to finish executing, but during its execution, processes 4 and 6 arrived in the ready queue. Because of this, the queue needs to be sorted again and time quantum is recomputed. Then P6 and P3 were able to finish. During P3's execution, another process arrived in the ready queue. This causes the program to sort the array again and compute the quantum time, then execute each process accordingly. Here is the Gantt chart of the example. Let's compare the regular round-robin's result with a modified round-robin algorithm. Response time was improved by 5.6 milliseconds, while turnaround time and waiting time were improved by around 36.6 milliseconds. Here is the graphical representation of the table. The modified algorithm has already shown improvements to the round-robin algorithm, but it can be improved a little more by skipping the sorting of the ready queue if no new process arrives in the ready queue. This is because, after a completion of a cycle, when all processes have used the CPU for a time slice, the same processes in the ready queue are still in ascending order. Instead of sorting, the algorithm will proceed to the computation of the new time quantum.